third-year student in the environmental engineering school here at Mercer. My project is entitled Biosand Filter Engineering, and we're exploring the multifaceted aspects of poverty that we observed on the Mercer on Mission trip this past summer in Sasit, Kenya. Just a couple of acknowledgments that I wanted to throw out before I really get into the project data that was analyzed. Wanted to give a special thank you to Dr. Lackey, who's been informative and also just inspiring in the process. She's helped to connect me with bigger issues of poverty and to see how engineering plays into those as more of a socioeconomic issue rather than purely a technical issue. And so I wanted to thank her for that. And there were 4 other students who participated in the Mercer on Mission trip program that were part of the Mercer University School of Engineering. They were Aaron Brett, Keith Cicatello, Christy Hutchinson, and Katie Safford, and they were all extremely instrumental in collecting data and had just as much a part of that as I did in the data collection process, and so I wanted to thank them for that. Also wanted to thank Sam Harrell, who's the host for the Mercer on Mission trip in Kenya. He's a great partner and partners with villages like Sasit and other communities like it throughout the year. This is an overlay from Google Earth of the village of Sasit, just to give everyone a little bit of idea of the data range that we were collecting. This is an overlay of satellite imagery, and you can see that what we did was took pictures of where every biosand filter was located, and we labeled those by name. And so we would take an index card, write the name of the household on there, take a picture of it. The camera that we were using was programmed with GPS coordinates, and so it had GPS capabilities in it. From there, we were able to enter the GPS coordinates into Google Earth, get an overlay of where all of the houses were located, as well as the community center, different collection points, and things of that nature. And so that was useful for analyzing the data, as you'll see a little bit later on. The purpose of this project was to investigate how socioeconomic factors played a role in influencing the performance of biosand filtration systems in Kenya. Data was collected from 24 pre-existing biosand filters. In 2010, students participating in the Mercer on Mission trip to Kenya constructed 24 biosand filtration systems. Going back this past summer, we constructed an additional 24, but we also had a twofold process in that. The second part of that project being to collect data from the 24 pre-existing filters. 3 types of data were collected. We had technical data, and that includes things like coliform removal. Geographic data, we used that in our Google Earth software, and through that we could trace lines and measure the distance from house to collection points, house to community center, and things like that. We also collected socioeconomic data. This was on a relative affluence basis. We had different population data for each house and things like that. When possible, objective data was used for comparison purposes, and that means that actual numeric data, so percent removal, number of people in a house. When other circumstances permitted that not to happen, such as subjective data like the relative affluence of a household, a Likert type scale was used. It's basically a 1 to 10 scale, with 1 being, in that case, not affluent, 10 being very relatively affluent. So that's sort of the breakdown of the project there. I want to talk about some of these results and just discuss a little bit of the cool findings that we had in this project. A somewhat inverse relationship was found to exist between the distance a filter was located from the collection point and then its actual coliform removal percentage. And so this graph represents the distance that a filter was located from the collection point. We see that the smaller houses are close to just about 0.05 miles away from a collection point, and as you increase, there are houses that are closer to over 0.3 miles away from a collection point. And you see as that distance increases, the overall coliform removal percentage decreased. It had an R-squared value of roughly 0.7, so it was not a perfect relationship, but it was pretty good. You definitely could see the trend as distance increased. This is pretty self-explanatory for anyone who's studied biosand filters, and I realize that severely limits the population of this room, so I'll explain it just a little bit. Biosand filters are best used when they're used on a daily basis at least 2 times a day. And so if you're not using the filter at least twice a day, meaning dumping in a large bucket of water into the top of the filter performance will decrease over time. And so for longer distances away from a community site, the probability that someone is going to make multiple trips to go collect water a day is lower than if the collection source was near the home. And so it makes sense that as that distance increased, the trips of water would decrease, and therefore the coliform removal percentage would also decrease over time. And so you can see from the 2-year planning window that we had, where data was forming between the time that the filters were built in 2010 and then the time that we collected data in 2012, we see that that's the case. The most staggering relationships were those related to a BSF's or biosand filter's proximity to the community center. We saw that that was the factor that seemed to have the most determination in whether or not a biosand filter was going to work properly or not. And I want to talk about why we chose the distances that we chose. Approximately 50% of the existing biosand filters were located within a quarter-mile radius from the center of community, the other 50% being outside of that radius. And so it was a nice even split for data analysis purposes. And I want to talk about a couple of the things that we found there. Here's a graph showing a couple of Likert analysis and also number of fails. We have mechanical integrity, aka were the filter parts in good working order? Was it missing part of the filter? Was a pipe spout broken? Different things like that. On a scale of 1 to 10, the average mechanical integrity for houses within a 25-mile radius was 6.1, with that of over a 0.25-mile radius being about a 2.5. Similarly with sanitary storage, aka the water comes out of the filter and it may be clean, but then if it's stored for later use, if the container's not clean, with chickens and other livestock running around these homesteads, the water can actually turn out being worse than when you collected it from the river. And so the average sanitary storage on a Likert scale analysis was about the same as mechanical integrity, 6.2 for houses that were within a 0.25-mile radius and 2.5 for those outside of that radius. And then lastly, the number of filter failures, aka the number of filters that when we showed up to observe the houses were no longer in working order. There was only 1 within the quarter-mile radius, but there were 6 outside of that. With 24 filters, approximately 50% of the houses that were outside of that quarter-mile radius had malfunctioning filters. This is a coliform percent removal. Approximately, the average coliform removal percentage was 85.5% for those that were within the quarter-mile radius, and then it was 37.6% for those outside of that. So you can see that there's a staggering difference between the percent removals for those filters. Lastly, I wanted to talk about the relative affluence, and although this is not directly related to filter performance, there is something to be said for this, that the average affluence on a scale of 1 to 10, with 1 being not very affluent, 10 being very relatively affluent, was 6.9 for those houses that were within a quarter-mile radius, but it was only 4 for those that were outside of that radius. And so we see that looking into it, it would be pretty easy to say, okay, well, the affluent households have good filters, the non-affluent households don't have good filters, and that's true, but examining some of the data and some of the relationships that may sway those things, it's easy to see that there's more that goes into affluence and filter performance than just technical factors or just socioeconomic factors. It actually turned out that a closeness of a homestead to the center of community was a huge deal, and that's going to be key in moving forward in examining global poverty issues throughout the developing world, realizing the role that community plays in those developments. That's it for me. I just wanted to give you a brief summary of what my project was about. I wanted to ask the maswali, which is Swahili, for are there any questions? Yes, sir.
Were these filters, the 24 new ones that you built last summer, were they all built within that quarter mile, or were some of them still built outside of it?
I'd actually say that a lot of those were built outside of that quarter-mile radius, from having hiked about 2 miles up a mountain some way to get to one. And so a lot of those were actually built outside of that radius. These results will definitely change up, I'm sure, how Mercer on Mission approaches filter construction. Maybe not so much in, okay, we're not going to build these out of a quarter-mile radius, but it'll probably incorporate more education for those people who are outside of that radius. Yes, sir?
How did you determine which house was an affluent house Did you ask them how much they made?
That's an excellent question. We used a technique called asset mapping, in which we asked the families just questions about, hey, what kind of livestock do you guys have? How many people are in your house? We made visual observations on, okay, here was a bed here was a chair here. We saw goats, we saw chickens, we saw that the family had a homestead. And so it was a dual process of asset mapping. One aspect of that was that we asked the family questions about the assets that they had, and the other part of that was that we made visual observations as to the assets that they had.
Another question, actually.
Yeah.
Can you go back to that map where you overlaid it on Google Maps? Actually, rather, what was the actual scale of that map? How far out did you guys travel for all of these things?
So,
Like, what's the distance from the furthest left one to the furthest right one on
right.
this map here?
I'm not sure, man, to be honest with you. I know that, like, this distance to this distance, the community center, was approximately a third of a mile, if that
Okay.
scales it for you a little bit.
Okay, yeah, thank you.
What you probably can't see there is that it's mountainous.
Very. And that's
Yeah.
the thing is that it's hard to, you'd want to do a little bit more observation onto the terrain of a feature as well, which would be a future suggestion for this, is that distance is one thing, but a tenth of a mile distance that's up very steep elevation is probably harder to walk than a 0.25 mile distance that's relatively flat.
Thank you very much, Davis. I have one comment. So we think in English units, and I completely understand that. I can visualize a quarter of a mile. And if you tell me 400 kilometers, I instantly think, well, that's about 400 yards. So, you know, because I know that's how we think. But when you get into these professional publications, we need to have it in metric.
Okay.
And then with a bracket for the English so we can think of that. So that's just standard, formatting for
Okay.
technical papers. So before you get too far down the road and have to go back and convert everything.
That makes sense. I appreciate that.
Thank you.
Thank you.
So Davis just spoke to us about the socio-economic aspects of these